All right, thank you all for coming here. So I'm actually glad that Arjun went first because this paper is also about discrete choice demand, and so he's kind of reviewed a little bit of it for you. Um, but so this is a paper joint with two of my co-authors, also with the Federal Trade Commission. So the main kind of big picture question here is, how should we predict consumer demand? So there's a classic econometrics approach. So I have the Cowles Commission, which is an old commission from 50 or more years ago. But the idea here from them was, here's how you should predict demand. First, you should write down an economic model. The economic model should tell you what variables are important. Then you should turn that into an econometric model by imposing things like distributional assumptions on the error term, distributional assumptions like linearity, and then you use something like maximum likelihood to estimate demand. Okay, so that's sort of the classic economic approach. That's what economists typically do. There's a new approach. Bryman, 2001, calls this the algorithmic modeling culture. But the idea here is that true demand function is a black box. We're just going to use different algorithms to try to approximate it, and we'll try to see which algorithm best approximates it. Right? So that's what people typically do in machine learning. And I think those of you who are machine learners would probably say, if we care about prediction and predicting demand, machine learning is going to beat econometrics. So the point of this paper is, what are the limits of machine learning? So in particular, if you have big shifts in the choice environment, so the kind of products you can choose change over time, can a machine learning model predicted before the change correctly get what happens after the change? So that's the question of this paper. Susan Athey in Science makes this point as well, and she says there's a lot less attention on the limits of pure prediction models. We don't know how well they'll do if the choice environment is not stable. And so the idea here is, maybe machine learning models do very well in a stable environment when the set of choices stay the same. If you have major shifts in the choice environment, maybe they don't do so well. And for a lot of economic applications, we're really interested in what happens with a shift in the choice environment. So in this paper, I'm going to be looking at healthcare and in particular hospitals. And a lot of the concern in healthcare is there's some bargaining between a hospital and an insurance company. If they can't contract, the insurance company won't have that hospital in network, so the choice environment is going to shift a lot. And then the question is, what happens to demand, right? So if we want to predict what's going to happen in those negotiations, what's going to happen in a hospital merger, we need to be able to know what happens when there's a big shift in choice environment. So this paper is going to be an evaluation paper, and we're going to evaluate machine learning using large random changes in the choice set. So in particular, we have a bunch of hospitals that were destroyed or closed by natural disasters. So think about a tornado running through a hospital. We're going to estimate models before the disaster, see how well they predict after the disaster. So with any experiment, you've got to think about internal validity and external validity. In terms of internal validity, we're going to argue that the areas surrounding the hospital are relatively unaffected. So this looks more like just a shift in the choice environment as opposed to other things changing post-disaster. In terms of external validity, I'll show you that we have disasters in pretty different environments. So to the extent that we find similar conclusions across them, we think they might extrapolate more generally to, say, healthcare markets or hospital markets. So briefly, I want to talk about takeaways, given we don't have that much time. So what we find is, on average, machine learning models beat the econometric Logit model. So the kind of baseline we're going to think about is an econometric Logit, kind of like what Arjun was talking about econometricians have been doing for a long time. So on average, machine learning beats econometrics. But as we try to isolate to patients that had a big shift in the choice set, so they're likely to be really affected by this disaster, we find that the gap between the econometric model and machine learning models shrink. And sort of in the limit, that gap goes to zero. And I'll show you that in the talk. And so then finally, the question is, why would the economic model, say, have some utility when there's a big shift in the choice environment? We think here what's going on is domain knowledge. So in particular, a standard economic model going back to the 20s says that all the spatial differentiation is through distance, right? So if we're thinking about hospital choice, this is how far are you from the hospital. And that, on average, the machine learning models are not using that. They're just using general spatial differentiation through zip codes. And we think that when there's a big shift in the choice environment, having that parametric structure through distance is helpful in a way that maybe it's not so helpful when there's no change. So first, let me talk about the disasters. So we've got 4 disasters here. So we've got 2 tornadoes. There's a tornado in rural Georgia that destroys Sumter Regional Hospital. and another one in the suburbs of Oklahoma City that destroys a little small hospital. So these are 2 tornadoes in a rural suburban environment. We've got an earthquake that hit Northridge in January 1994 and destroyed St. John's Hospital, which is one of the 2 hospitals in Santa Monica. So this is a major urban environment. And then finally, we have Superstorm Sandy that hit New York, and this took out NYU Langone Hospital, which is one of the top hospitals in the country. It's a big academic medical center. It also took out Bellevue Hospital Center, which is the big public hospital in New York, and Coney Island Hospital, which is a regional hospital. So you can see that the environments we're looking at here are pretty different. There are different types of disasters. There are different types of hospital markets. So I'm going to show you one map. Unfortunately, we don't have that much time. But here's one map of what's going on. The purple areas here are the different zip codes in our data. And then the green line is the path of the tornado. And what's going on here is the tornado is going through rural areas, then it goes through the town of Americus, runs through Sumter Regional Hospital, and then goes out through other rural areas. So you can see, if you just look at the map, that there are a lot of zip codes where there's no disaster damage at all because the tornado never went through those zip codes. And so what we're relying on for this experiment is that there's a change in the choice environment because Sumter Regional disappears, but a lot of the patients surrounding are not really affected by the disaster when they're making their choice, other than one of their choices disappears. In the paper, we talk a little bit more about when this might be more or less true and try to isolate the people where we think it's true. We find similar results. So the baseline framework, Arjun already showed you this equation. This is just a Logit equation. So here we're talking about patient I going to hospital J, and that probability just has a very simple Logit form, where delta ij is the deterministic utility for hospital J for patient I. So the big advantage of the Logit is counterfactual prediction is straightforward because of the IA property that Arjun talked about. So the big question is then, how do you choose delta ij? So the standard econometric models has been to pre-specify a functional form for delta ij, which I'll share in the next slide, and estimate that using maximum likelihood. But you could think about machine learning models that we're going to recover delta ij algorithmically. So let me go to the parametric Logit model. So this is a Logit model, but I don't want to go over the math. I'll just go over the intuition here. The intuition here is there's 2 basic things going on. First is that there's horizontal differentiation through travel time. People tend to go to hospitals that are located close to them, and how long it takes you there is a sufficient statistic for that. There's also vertical quality that we're going to proxy through hospital indicators. So there's just going to be some hospitals that people like a lot more than others. And then finally, there are going to be interactions with patient characteristics. So we're going to have emergency versus non-emergency patients, or older versus younger patients, or labor and delivery versus cardiac patients. So it could be somebody going in for labor and delivery is going to have very different preference than someone going in because they have a heart attack. So the model is going to allow all of that, and it's going to allow it through this deterministic linear type structure. And all the econometric models are some version of this type of structure. So this is going to be our baseline model we're going to compare things to. But then we've got a bunch of candidate machine learning models. So these machine learning models are not really imposing any economic assumptions. We're going to use a set of features. There's going to be patient characteristics like age, diagnosis code, etc. And then we're going to allow unrestricted spatial differentiation through zip code. Okay? And so we've got a bunch of models. I'm going to put them into 2 classes. The first are grouping estimators. So the first one is a bin estimator that we just developed internally because it's very simple. It just takes your zip code and a bunch of characteristics and puts you in a bin, estimates demand within each bin. Right, so you can think about it as that's an exogenous grouping procedure. And then the machine learning models are various different forms of an endogenous grouping procedure. So the first is a decision tree, second is random forest, third are gradient boosting trees. And if you look at the literature on machine learning, they tend to say decision tree is interpretable, but maybe not the best predictor. If you use a random forest or gradient boosting trees, those are very good predictors. So we're going to look at those 2. We're also going to look at a version of Lasso, which is a regularized multinomial Logit model. So this is going to pre-specify tons and tons of interactions. So this would be like a hospital indicator interacted with a zip code, interacted with an age group, or say labor and delivery, and you can include all of those as covariates and then use regularization to pick which of those to use. So we've got two types of machine learning models and several machine learning models to look at. The experimental design here is it's gonna be pretty simple. We're gonna estimate the models before the disaster. We're gonna examine their performance post-disaster, and we're gonna drop all the data in the month of disaster, right? So we don't want anyone coming in because of storm damage or something with a disaster. The main assumption here is that other than the choice environment changing, there's no difference pre-disaster versus post-disaster. So the prediction criterion I'm going to look at here is very simple. It's just the percent of choices that are correctly predicted. You know, we find similar results if you look at root mean squared error or something more sophisticated, but this is very simple. And then we're going to show the results relative to the Logit model, so relative to the econometric baseline. So the first graph here is the performance, the average performance across the disasters. So I'm just going to estimate the percent correctly predicted for all the models, average them across the 6 hospitals that were destroyed, and then show the percent improvement over the baseline Logit. So what we see here is, you know, the dashed line is at 0, so that'd be that the econometric model and the machine learning models are the same. And we find the machine learning models are a lot better. So on average, the random forest model and the gradient boosting model, so that's RF and GBM on the graph, are about 20% better. Then if you look at the regularization model, that's about 17-18% better, so close, but not quite as good as the random forest and gradient boosting. And then like an exogenous, say, semi-parametric bin estimator is much worse. So still better than a Logit, but much worse than the machine learning models. Right, so on average, it looks like machine learning wins. If we look at this by disaster, so here we're showing the regularization, gradient boosting, and random forest models, we find that the machine learning models are better for 5 disasters. The sole exception is the Sumter disaster. I'm going to get to that later in the talk, but the big difference between the Sumter disaster and the rest is that the Sumter disaster had a much bigger change in the choice environment. So Sumter Regional Hospital had about 50% market share pre-disaster, whereas in the other cases, the market share was about 10 to 20%. So in general, patients faced a much bigger change in the choice environment for Sumter than the rest. And if you look at the figures here, Sumter is the only one where we see that the Logit and the machine learning models are similar. For the others, the machine learning model does a lot better. This is a CS talk, so I'm going to talk about computational time very briefly. And what we find is that so St. John's is the sort of the largest data set, Moore is the smallest data set. The random forest is extremely fast. So it's about 6 minutes for St. John's, about 1 minute for Moore. So if you think about it, not only is it doing a better job of predicting on average, it's also extremely fast, right? So if you think of that as a criterion, it does very well. But now we're going to focus on patients that had a large change in the choice set. So these are people that we think were really affected in their decision by the destruction of the hospital. So we're going to proxy this by 2 ways. First is for New York and California, I have data on whether you went to that hospital previously. So we're going to just focus on patients that previously went to the destroyed hospital, see how well we predict for them. Second, you can use the models to sort of predict who would have been likely to have gone to the destroyed hospital if it hadn't been destroyed. So we're going to look at patients with a large predicted share of going to the destroyed hospital. So that's another way to proxy for you were heavily affected by the disaster. So the first graph here is previous patients. So the red line is all patients. The blue lines are previous patients. And what you see is that the gap between the econometric model and the machine learning model shrinks when we look at previous patients. So if you look at random forest or GBM, they're about 15% better. So remember, this is just New York and California hospitals. They're about 15% better for all patients, but only about 5% better for previous patients. So essentially that gap has shrunk considerably once we look at patients that previously went to the destroyed hospital. Next, I'm going to look at subgroups by the share of the destroyed hospital, the predicted share of the destroyed hospital had not been destroyed. So here, red are people where the probability they would have gone to destroyed hospital using the bin model is less than 10%, and blue is people whose probability is greater than 30%, and we see a sharp deterioration, right? So for people that their probability of going to the destroyed hospital is less than 10%, the machine learning models are about 25% better. If we look at people whose probability was above 30%, that gets cut in half to about 12% better. Now I'm going to look at this specifically for the Sumter disaster, and that's because that was the one where the destroyed hospital had a 50% share. And so we can look at people that were extremely likely to have gone to the destroyed hospital. So here, if you look at the purple and blue lines, those are people with really high probabilities of going to the destroyed hospital. Green and red are people with low probabilities. What we find is that if you look at people with high probabilities of going to the destroyed hospital, the GBM model is strictly worse than the econometric model. The random forest is about equal to the econometric model. So once we look at patients that are very likely to have a big change in their choice set, there's not much difference between the econometric model and machine learning model. I've got 2 minutes left. So in the last couple minutes, I want to talk about, why is it that we find that the machine learning model's relative performance drops when there's a big change in the choice set. So there are a couple of potential explanations. So first is that post-disaster, you need a less local model. So the machine learning models are very local. They're fitting very local preferences. You need a more global model post-disaster. Another one is that post-disaster, the domain knowledge is more helpful. And so the fact that the machine learning model is imposing that spatial differentiation through distance is a lot more helpful when there's a big change in the choice environment. So we're going to examine this by varying the random forest node size. So we're going to have one specification which has a large node size, so it's a less local model. Another with a small node size, that's a more local model. If we do that, what we find is that, so I'll just show you the results for Sumter. If you look at the small node model, we find it does about the same as the Logit models. If we look at the large node size random forest model, we find it does strictly worse. So it doesn't seem like using a sort of a more global model helps. It looks like this is actually because of the domain knowledge, which in our case is because of distance. So just to conclude, we find machine learning models do better on average, but we find that performance declines when there's a large change in the environment, and it looks like domain knowledge is useful when there's a big change in the environment. So hopefully my job won't be automated away by a machine learning model.